Okay, so now let's dive into the numerical technique. Okay, so the Euler equation, done, it was fast. Now the numerical technique, the so-called finite volume approximation. So now again, very abstract. We have capital U, vector of conservative variable. Remember, density, momentum, total energy, three components for the vector. And F, the flux vector, right? The flux of mass, the flux of momentum, and the flux of total energy, right? They've been presented previous slide. So now what we're going to do is we're going to discretize space with this little volume element. So this is 1D, of course, right? So you discretize with the boundaries. Here, what's important here are the boundaries. And inside those two boundaries, you have a volume. Right? And so this point here has no meaning. It's just shown to kind of identify the volume element, but it doesn't mean anything, right? As opposed to the finite difference method, where the solution is defined at the point, but not here. Here, the solution is defined as a volume average inside this volume. And so there is no point. You just have to consider the entire volume. Okay, so here, the notation here, so I is for the index, the cell index, right? You see the cells are moving from 1 to n. The box size goes from 0 to capital L. And you integrate the solution, density, momentum, total energy, into this volume. And then you divide by h being the size of the mesh. Okay? And this defines a volume average, hence the notation, the bar above, right? It's a volume average. Okay? And n here is for the time step, right? So that's at times Tn. Okay? So that's the finite volume approximation. So we approximate the solution. So inside the volume, the solution can be very complicated, right? It can have a lot of structure and stuff. No, we average everything by half. Okay? So that's the approximation. So now you can actually integrate in time and space your partial differential equation, your conservation law, dx dt equals 0. And then if you do this, obviously you want to integrate in time this guy first and integrate in space this guy first, because it's easy. They are derivative in time and space, so the integration is easy. Right? And then, of course, you have to perform the second integration, and then you land on this equation, which is an exact result. It's called an integral form, and you recognize here the definition of the numerical approximation, right? And here you have a new guy, a new object, which is the flux at the boundary of the cells, right, which are those guys here, and integrated in time. Okay, so this is an exact equation. There is no approximation, right? That's very important to realize. We have just integrated both in space and time the conservation law. And you see that that will be our numerical algorithm. That's how we're going to update the solution at times n to the solution at times n plus 1. Okay, the only catch is that we need to compute this time average flux. How do we do that, right? Okay, so that's the beauty of Godunov method, right? Which was invented in '74 by Godunov, a Russian scientist. So again, I show here the definition of this flux. So it's a time average of the flux at the interface. Okay, and so Godunov had the idea that if you consider that your solution is piecewise constant, so that's the big approximation here, right? So you assume that the solution as a function of x now is not a complicated solution, but it's flat, right? So it's equal to the average. Then you have two piecewise constant states, one on the left of the interface, one on the right on the interface. And here the magic happens. We can compute the exact solution. It's called the Riemann solution, or it's called the solution to the Riemann problem. That's called the Riemann problem. You have a left constant state, left constant density, velocity, pressure, right constant state, density, velocity, pressure. This can be solved exactly. There is an exact solution for that, meaning that you can compute the solution. So here, that's the solution. And it's self-similar. That's the beauty of the Riemann solution, meaning that you can actually now evaluate this flux at x equals 0, which is at the interface, And at t equals 0, actually at x over t equals 0, is going to be constant. So if the flux is constant, it means you can take this constant out of the integral, and then poof, you have the result. Okay, that's the beauty of the Riemann solution. It's self-similar, meaning that now you can replace this integral by a constant value, which is given by the solution of the Riemann problem, right? So you still have to solve the Riemann problem. That's expensive, but then you have the flux. You have the exact solution, meaning now you can update your volume average and reach the next time step. Okay, so that's the good enough method, right? It's the summary. At initial time Tn, you assume that your volume average quantities are actually the solution, so piecewise constant. You solve the intercell flux between the two left and right piecewise constant states. That gives you the good enough flux. And then you update the solution using this equation. Right? Yeah.
Sorry, what does it mean to be piecewise constant?
So it means that if I plot my little volume element, okay, these are my cells. That's the left boundary of the box. That's the right boundary. Your solution, for example, the density, right, is like that. That's piecewise constant.
So that's totally unphysical.
The exact solution, the underlying exact solution might be like that. And you approximate your smooth, detailed solution by piecewise constant values, which is the numerical approximation. And obviously, it depends on the size of the mesh, H. And if you have a very fine mesh, your solution will be more accurate. But that's the key point, right? If you assume that your solution is piecewise constant, you're making an approximation, obviously, to the truth, which gives you an order of accuracy, which you can show it. I'm not going to show it here. It's first order accurate, meaning that your error is of order H. You're making an error which is proportional to H, the size of the mesh, right? So that's the price to pay to make this piecewise constant approximation, right? Is to have an error, a numerical error, which is of order H. But once what's nice in the good enough method is that if you adopt this piecewise constant representation, then all the different steps are exact. And of course, the error that you're making is to, represent this complex, possibly very complex solution by a piecewise constant finite volume approximation. Okay, so just to a few facts. What's beautiful is that this method that I just described, which is quite simple, is valid for any nonlinear system of conservation laws as long as they are hyperbolic. The main expensive component that I have kind of ignored so far is the Riemann solver. We call it the Riemann solver. So how do you compute this flux? That's the most expensive step here, right? And how do you do that? I told you there is an exact solution. Okay, but how do I compute it, right? And that's expensive, right? I mean, hopefully, I will show you some approximation. You can do some approximation of the Riemann solution so that your Riemann solver is fast. And of course, it's going to be an approximation, right? But since you're already doing an approximation by adopting a piecewise constant representation, you might as well approximate the Riemann solver too, right? Okay, yeah?
Sorry, what does it mean up there, valid and exact? Just because we do keep talking about approximations, what does exact mean here?
So exact means that if you start with piecewise constant, all these are exact. There is no approximation. The only approximation is to assume that it's piecewise constant. All the rest, it is exact. Okay, that's the power of the good enough method. And of course, the weakness of the good enough method is that it's piecewise constant. Okay. So there is a stability condition. I'm not going to spend too much time on that, but there is a stability condition here which is that the time step has to be smaller than the cell size divided by the largest eigenvalue of the Jacobian matrix, which are also the speed of the waves. When you have a hyperbolic system of conservation law, it means you have waves, and those waves have a speed. And the idea is that this condition is basically the same as saying that when you have one Riemann solver here and another Riemann solver nearby, you don't want the two Riemann solvers to interact with each other, because then they're going to change and the value will not be exact anymore. So in order to decompose your problem into independent exact Riemann solvers, you want to make sure that the waves are not touching the other Riemann solver, the other Riemann solution. Right? So that's the stability condition. Right? That's what I explained. So two neighboring Riemann problems cannot influence each other. Otherwise, it's going to be wrong. Right? Okay, so that's okay. So now let's consider a very simple example, which is the advection equation. So it's the simplest PDE you can think of. It's hyperbolic, and A is the speed, the advection speed, and it's a constant. So it's a linear PDE. And U is anything you want, density, concentration, chemical concentration, whatever. And so what this equation describes is that you're advecting, you're moving quantity U with velocity A. And if you choose A positive, then you're moving to the right. So very simple. So now let's write the finite volume method. So that's the finite volume approximation for U. U is a scalar. Huh? It's not a vector anymore, it's a scalar. And that's the numerical representation here. And then that's the integral form. That's the exact update. We just need to compute the flux. Right? And the flux here, in this case, again, comes from a Riemann problem. But the Riemann problem is very simple. In this case, the exact solution is very simple. So that's the Riemann solution. So in black, that's your initial, piecewise constant left and right cell. And what is the solution to this Riemann problem for the advection equation? Is trivial. You just move to the right by A, at velocity A, right? And so the red solution is the solution to the Riemann solver, to the Riemann solution. And you see now that the flux that you have to take here at this boundary between the two left and right cells is actually the left value, because you move to the right. So the value you have to consider here is actually the red cell here, which is you take the left value. Okay, meaning that the solution to the Riemann problem is, if the velocity is positive, it's the left one. So F at the boundary is actually A times the left value. Otherwise, if the velocity is negative, the Riemann problem will go in the other direction, and you're going to take the right value. Okay? So that's the example, the simplest example. To solve the advection equation, you just have to basically, the exact solution to the Riemann problem is really simple, and it's just this. And so this is called the upwind solution. Upwind because if the wind flows to the right, if A is positive, you're going to take the left value. So it's the value which is upwind. If the wind flows to the left, then you're going to take the right value, which is also the upwind solution. So you always take the upwind value to give you the flux. Okay, this is called upwinding. It's the key concept of the Godunov method. And so what's nice, actually, you don't see it, but you can see it in your slides. Depending on the size of the sign of A, you can write this flux, right? This flux here. You can write it in a compact form like that, without, writing up a test, like a condition like that. You can write it directly like that using the absolute value of A. Okay, and that's the key point to understand, right? Is that this numerical flux, this Godunov flux, contains two terms. This guy here, which is the average of the two left and right flux, and this guy here, which is UR minus U left, which looks like a diffusion operator. This is exactly like minus nu, diffusion coefficient, times the gradient of u, the unknown. And so you see that you have two terms. You have one term which is actually the average of the two flux, which if you use this for the flux is going to be unstable. You don't want to do that. But there is a second term here, which comes from the upwinding, which comes from the Riemann solution, which actually gives you the stabilizing term. So this is unstable. This will stabilize the numerical solution. And this is actually like a diffusion. So you have the physical intuition that if you have diffusion in your problem, things will be a bit viscous and more stable. Right? That's exactly what this upwinding, which is the exact solution to the Riemann problem, right? That's exactly what this upwinding does for you. It makes the solution stable. Right? Unstable, stable, all good. Okay, that was the advection equation. So now let's move to a slightly more complicated problem, right? Which is now a system of hyperbolic conservation laws, but still linear, right? So it's linear because now A is a constant matrix, but now it's a matrix. So for the Euler equation, for example, it's a 3x3 matrix. Right? And remember, so U, for example, can be the density, the velocity, and the pressure. And A is the constant matrix. So let's go back to the Euler equation in quasi-linear form, right? So that's exactly where they come from. If you now put V, rho, and P, those guys which are outside the derivative, equal to constant values, rho naught, V naught, P naught, and you let P, rho, and V as the perturbation with respect to rho naught, V naught, P naught, you have a linear system. That's why this form here, which is an exact form of the equation, no approximation, it's called quasi-linear form because it's very easy to linearize them immediately by putting everything which is outside the derivative to constants. And then you end up with exactly this form here, where U is rho, V, P, right? And A is the previous Jacobian matrix, but with rho naught, V naught, P naught, constant coefficient. So again, we use the Godunov method, right? So now the flux is actually very simple. It's a constant matrix applied to U. That's the Godunov update. And now we need to solve the Riemann problem, right? And so now there is a little bit of magic here, which is that, remember that we have a hyperbolic system of conservation law, meaning that A has real eigenvalues and associated eigenvectors. Okay, again, it's very abstract on purpose. So it means that you can project U, the vector of conservative variable, into V, the vector of the eigenvectors, right? So that the matrix A, if you transform the matrix A into the basis of the eigenvectors, becomes diagonal, right? And this is like eigenvalue decomposition 101. I hope you're familiar with that. You have seen this in high school, I think. And so D, what is D here is actually a vector that contains all the eigenvalues, right, of the problem, right? So here, what's the beauty with the linear system is that if you multiply your equation here by L on the left and R on the right, which is the basis transformation from the original basis to the eigenvector basis, you end up with a diagonal, three diagonal independent PDEs, right? So you can actually now solve each of these three independent linear problems independently, right? And we know how to do that. It's the upwind solution. And then once you have solved the Riemann solver in this eigenvector basis, you go back to the original basis and you get the Godunov flux. And the Godunov flux looks like that in the compact form, right? So you recognize the unstable term here and the stabilizing term, which looks like a diffusion, except now you have this notation, which is that you go to the left. So you go to the basis. Now you take the positive eigenvalue, which is the upwinding, right? and then you go back to the basis. So that's your Godunov flux. So you have an explicit form for the Godunov flux, which requires you to perform the eigenvector decomposition. Okay, that's the Riemann solution for this linear problem. So let me explain a bit more. So if you start from this where A is a matrix, you project this equation into the eigenvector basis, you end up with this now problem where now D is a diagonal matrix. Okay, and D is the diagonal matrix where the lambdas are the eigenvalues. Okay, so now it means that you can now, if you write alphas as the eigenvector component of your solution, then that's what you get. You get you get n equation like that, which are independent. And we know how to solve this. It depends on the sign of lambda j. If lambda j is positive, then we take the left value. If lambda j is negative, we take the right value. That's the upwinding. Okay. And once we have the solution in the eigenvector basis, so we have the Godunov solution for the alphas, left or right, depending on the sign of the lambdas, then we can go back into the original basis by applying matrix R, and we get the flux. Okay, that's the trick. Okay, so that's the Riemann solution for a linear system. Okay, so here I'm not going to do it because I don't have time, but here I have a few slides where I apply this technique for the Euler equation, the linearized Euler equation, right? So that's the matrix A, V naught, rho naught, P naught, right? The constant state. And then the perturbations, delta P, which is P minus P naught, right? So it's P if you want. And then I do the eigenvalue decomposition. So you're gonna have to do it at home. Then you have, that's the representation here. So that's X space, and that's time, right? So that's a space-time diagram, it's called. And each of those eigenvalues represents a wave that travels at a given speed. Right? Remember, eigenvalues are speed. And so you see here the right eigenvalue, which travels to the right, the intermediate one, and the left eigenvalue that travel to the left. And depending on the sign of those eigenvalues, the Godunov state, which is the one in between, the one that you need for the flux here in the middle, is going to be the left or the right, depending on where this eigenvalue is traveling. Okay? And so you see that, for example, if you want to compute the density, you're going to have to project back to the original basis, and you take the left value for those two right traveling waves, right? Because you have to take the left one because of upwinding. But for this guy, you take the right value because it's traveling to the right. So you see that your flux is a combination of two left states and one right state. Okay, that's what this kind of eigenvalue decomposition does for you. And so in the jargon of the Godunov method applied to the Euler equation, you have what is called the left region, which is totally untouched here. You have the right region, which is the totally initial right state. And then you have in between the star region, which is the result of the interaction of these different waves. And the Godunov state in the middle is taken by, in this example, right? That's just an example, because those three waves can have, the free can be on the left, the free can be on the right. It depends. It depends on your matrix A. Right? Okay, so so now for the Euler equation, for the nonlinear Euler equation, things are more complicated now because the problem is nonlinear, right? And now we have a lot of ugly waves. They are not nice little linear waves like we just did, right? Which are, by the way, sound waves or vection waves, but constant speed, right? Now, with the nonlinear Euler equation, we end up with much more complicated objects, which are nonlinear waves. And this is one example. So again, you have three waves. That's good. That's the similarity with the previous problem. But one of the waves in this example is a shock wave. So it's not a sound wave anymore. It's a shock wave. It's a discontinuity. You have in the middle a contact discontinuity, which is basically the, if you want, it's the same as the chemical composition of the initial left and right state. And then on the left, again, that's an example. you have a rarefaction wave, which is a complicated nonlinear wave that describes the expanding wave. So I'm not going to do that by lack of time. But if you're interested, I will give you a reference and you can dive into this physics. If you're interested, that's really hardcore. The key point is that if you manage to understand all this and you can solve this analytically, this is all analytical solutions or quasi-analytical, you can solve the problem exactly and find the Godunov flux, right, which is the flux at this boundary. Right? So that's called the exact Riemann solution of the Euler equation. And that's, the Jupyter notebook that I gave you contains all the algorithm to do that. So you can have a look. And I'm not going to do it here. Okay, let's now summarize the Godunov method for the Euler equation. Right? So again, vector of conservative variable, density, momentum, and total energy. So usually what we do is we convert this conservative variable into the primitive variable. Remember the primitive variable, density, velocity, pressure. So how do you convert this? In this example, you don't do something fancy. You just take the momentum, you divide by the density, you get the velocity. Okay, that's kind of the definition. And for the pressure, you just get the total energy, you subtract the kinetic energy, you multiply by the gamma minus 1, the equation of state, you get the pressure. Okay, so those primitive variables, why do we use that? It's because it's much easier to manipulate. All the basic equations are expressed in the form of the primitive variable. For example, the sound speed, which is the speed that goes into this eigenvalue decomposition, is gamma p over rho. Right? So you can compute the sound speed using the conservative variable, of course, but it's more ugly. Right? So this is much simpler. Then you compute the time step. Again, you don't want the Riemann problem to interact with each other. Right? So the time step has to be smaller than h over the largest eigenvalue. And you put a c here, which is less than 1, right, to avoid the interaction of the wave. So let's put 0.8, right? And then you know that the time step will be small enough. Right? So the method will be valid. Okay, now you have the conservative variable everywhere, the primitive variable, sorry, everywhere. So you can define your Riemann problem, the piecewise constant Riemann problem at each interface, using your exact Riemann solver that you know how to get. Right? That gives you the flux. And then you update your solution. Your conservative variable are updated from times n to times n plus 1 using this flux. That's the Godunov method. Okay, so just to give you an example of how well it performs, so that's a very famous test that you're probably going to do tomorrow afternoon multiple times, in multiple form. So it's called the SOD test. It's basically a Riemann problem. Right? So the initial conditions are two piecewise constant states, left and right, that you can read off. Actually, it's the unperturbed value on the left and on the right for each of the variables, density, velocity, pressure, entropy. I mean, entropy is redundant, but these are the three variables. The unperturbed states that you see here and here are actually the initial conditions. Right? And at t equals 0, those two, this discontinuity is, let go. And then you see a rarefaction wave on the left. You see a shock wave on the right here, and the contact discontinuity here in the middle. And that's how the Godunov method, the first order Godunov method, performs. Right? So it's pretty good. Yeah.
Yeah, I understand about the Godunov method. And in one time, we will need the left and the right state.
Yeah.
But in one grid, at the end of the grid, at the edges, we will not have left or
totally.
right state.
Totally. So that you're right. Very good question. I don't have time to discuss this in detail, but that's called the boundary condition. And that's very important. Right? And so here you need to come up with a boundary condition. And in the Jupyter notebook, you will see there is a special function which deals with the boundary condition. And you have multiple options here. Right? And of course, it depends on the physics of the problem. So here, obviously, a simple boundary condition in this case will be that you prolong the unperturbed solution to the left, right? And so you need to use ghost zones. They are called ghost zones, which are fictitious cells, which are outside the box. And then you have to give them a value. And depending on the strategy, depending on the boundary condition you want to adopt, this value, for example, will be equal to the value inside, or it can be periodic. If it's periodic, then this value out there will be equal to this guy. Then it's periodic. In this case, periodic is bad, right? Because you can have also reflexive, right? So if you have a wall, for example, here, you can mirror the values of the density, velocity, pressure with respect to
the quantities.
Exactly. All the quantities, you have to adopt a certain definition, strategy to define your boundary condition outside the domain, totally. Because you need the flux here. You need a flux here.
Yes.
Yeah. And so that's how you do it. You use ghost zones, ghost cells.
Thanks.
Okay, so just a few comments. So that's the shock, and the shock is like really good, right? You see that the exact solution is a discontinuity, right? And you see that the numerical code managed to, the Godunov method, sorry, managed to find this discontinuity just over 2 cells, which is kind of the best you can do, right? Then here you have the rarefaction wave. So it's not perfect. Huh? Rarefaction wave, you can see that it's kind of very smooth here. And you kind of miss the solution by a little bit, right? And this is first order accurate. So if you reduce the size of the mesh, so here there is, I think, 100-ish points. If you multiply by 10, then your solution is going to be much better, of course, right? But much more expensive. Right? So the other problem, and that's the main problem, is the contact discontinuity. You see how smeared it is. It's really ugly. So the contact discontinuity is another discontinuity, but the numerical code here doesn't really do a good job, right? So that's clearly the weak point of the Godunov method. The strong point is the shock. For example, you will see what SPH, which is the other method, does. It's not very good for shocks, right? But SPH is really good for contact discontinuity. Finite volume is the other way around. Very good for shocks, not so good for contact discontinuity. At least the first order method. Okay. Okay, so I'm gonna try to fly through the approximate Riemann solvers. So here I'm not gonna, enter too much the details. I'm just gonna give you the philosophy of the strategy to design these approximate Riemann solvers. Because as I said, I'm gonna repeat that. The first order Godunov scheme is not so accurate. You have seen what it does, right? It's kind of smooth and ugly. So why solving exactly the Riemann solution if it is to get such an ugly solution, right? And so the idea is to actually approximate the exact solution with reasonable models. So there is 2 types of approximate Riemann solvers. One which is linear Riemann solvers. I will show you how it works. It's very simple. And the second type is the so-called HLL family, which is based on very simple a very simple strategy to approximate the solution during the Riemann solver by piecewise constant states. Again, right? So I will just briefly describe the technique. So linear, actually, as the name indicates, you assume that your problem is linear, right? Which is wrong for the nonlinear Euler, but sometimes it's a good enough approximation. And if your problem is linear, then you know the exact solution is given by this matrix form. The upwinding of each eigenvalues. The problem is how do you compute in the nonlinear case? How do you compute the Jacobian matrix? You can't really, because you don't have a reference state anymore. You have a left and a right state, and they can be very different from one another. So how do you compute the Jacobian matrix, the reference equilibrium state? So there is a simple strategy, which is to take the arithmetic average, right? And that kind of works okay, but it's kind of unstable in certain solutions. But there is a technique called the row average, which is the row matrix. So instead of using this average, you use this average. Kind of weird. It's weird. Why that? Well, because there is some magic happening. Because in this case, if you use this linear matrix, you get back to the nonlinear flux for the left and the right state. And so that's something which is really powerful, the row average. It's a property, it's a weird property of the Euler equation that if you use this for the reference state for the Jacobian matrix, you get something very close to the exact solution. Right. So that's the row matrix. Then the HLL family. So here the idea is like really simple. You have a left and a right state. That's your Riemann problem. And instead of getting this complicated shape that you have seen in the SOD test, we assume that the star state is constant also. Right? So that's pretty approximate. So remember, that's the exact solution, right? So that's the left rarefaction wave. That's the right shock, right? The HLL family, you assume that all this is constant. So you have just something like that. Okay? So that's pretty extreme, right? And if you do that, then things are actually quite simple because you can actually compute everything by using the conservation laws. Right? So you use your conservation laws. And so I'm not going to do the math here, but you just apply these calculations here where you integrate both in space and time your conservation law. And because your states are constant, you can perform this integration exactly because it's very simple. There is no profile, right? So it's the flat thing. So you get this. And then you apply it a second time on the right wave, you get another relation that gives you the flux. And boom, you have the Godunov flux that comes out directly. Right? And of course, there is one complication, which is that you need to compute the left and the right speed. What are those? Right? And so here in the HLL technique, the speed are computed like that. Basically, you take the absolute left, the maximum left speed of the problem, given the velocity and the sound speed of each cell, and the maximum right speed that you can get using the same quantity. And that's it. Your Riemann solution is found. And that's the final algorithm, right? So it's pretty simple, right? You just have to compute the left and right flux, the left and right wave, and your algorithm is like 3 lines, literally 3 lines. And that's pretty good. So there are variants, so that's how it does, right? So that's again, I compare here the exact solution. So in red is the exact, no, wait. Yeah, actually I forgot which one is exact and which one is, but you know, it's close enough, right? So, I think the exact one is the blue one because it's better here at the rarefaction. So the exact is the blue one, and you see that HLL is doing this little mistake here at the tip of the rarefaction wave. It's almost nothing, right? But you have something which is like laser fast, right? Which is like much faster than the exact solution, which, as you can see from the Jupyter notebook, is really complicated. Right? So that's why in most cases HLL is enough. So there are variants of that. I'm gonna. There is HLLC, no time to discuss this. The key point now is that if you compare HLLC with exact, it's almost perfect. I think, yeah. So you see the shock is perfect, the discontinuity is perfect. It's only a little bit the contact that is not so good. Okay, so these are the different Riemann solvers, right? So that's the temperature of the SOD test. So you have 4 different Riemann solvers here. The exact one, which is in red, so that's the best one, right? You can see here. Then HLL, HLC. And you see the contact discontinuity is the hardest one to get. And actually HLLC, which is this last Riemann solver, is actually almost as good as exact. That's the take-home message here. HLLC is almost, right? It's only fading a little bit down there. But much faster.
Sorry.
Yeah.
So what's the difference between a contact discontinuity and shock?
So a contact discontinuity, the pressure and the velocity are uniform across the contact. And you can see it here, right? So that's the velocity. And you see that it's constant across the contact discontinuity. Same thing for the pressure. It's constant across the contact discontinuity. And the only discontinuous quantity is the density. A shock, everything is discontinuous. Density, velocity, pressure. So that's the difference. So a contact wave is really an advection wave. So it's exactly that advection equation. Because the density, the pressure and the velocity are constant, your Euler equation simplifies a lot, and you're just basically advecting the density. Right? While a shock, it's much more complicated. Right? You have a dissipation, and so everything is changing. Okay, so conclusion for the Euler equation. So that's really a powerful method for solving any type of nonlinear system of conservation laws. The only condition is that they have to be hyperbolic. Right? These conservation laws, hyperbolic, are found for the ideal MHD, relativistic hydrodynamics, radiative transfer with some closure, shadow water equation, which are for tsunami, traffic flow equation, which is for traffic in New York, and all these are hyperbolic system of conservation laws. Some of those systems are not strictly hyperbolic, meaning that they can have eigenvalues which are equal. Strictly hyperbolic systems, the eigenvalues are all different. So the Euler equations are strictly hyperbolic. Right? But ideal MHD, for example, they are not strictly hyperbolic. In some conditions, you can have eigenvalues which are equal. And that's a bit nasty. Right? So it's just to, this brings some complication. Now, Riemann solvers, remember, that's the main component of the Godunov method. But I think the message here is that forget about the exact Riemann solver. You don't need exact Riemann solver. It's a waste of time. Just use approximate Riemann solvers, and the best one is HLLC. It's the best compromise between costs and accuracy. And of course, you have the same HLLC type Riemann solver for all these kind of examples. In each case, you can design your HLLC Riemann solver or equivalent. So Godunov method, the finite volume Godunov method is great for shocks. The best. I cannot do better than that. You have this courant stability condition. You don't want the wave to interact, right? And as I will not show, I think, by lack of time, it can be very easily generalized to high order, right? Like second order, third order, fourth order schemes. So I will flash you a few results. And it's also quite easy to generalize to multiple dimensions. Right? So the technique, the methodology can be applied to multiple dimensions. So let me, in the last 4 minutes, let me flash you some.
10:30.
Say again?
Your time to 10:30.
Oh, okay. Sorry.
Started early.
Oh, great. So then we're gonna see all this. Yeah, it wasn't 9:30, the beginning.
I think you started 9.
Yeah.
You should start 9:30 to 10:30. Your time to 10:30. Yes.
Yeah. So I should have started at 9:30.
Yeah.
Okay.
That's fine.
Told you. I told you.
Chris told us 9. I will correct her. But yeah, your time to 10:30.
Okay, my God. So I'm gonna do everything. The school will be done this morning. Okay, great. So then I have much more time. Great. I have. So that's the book that I strongly encourage you to read this summer to learn more about the Euler equation, especially exact Riemann solvers. That's really the Bible by Toro. Okay, then I'm gonna show you some examples. So these are other tests that are all in the Jupyter notebooks. So if you can run them yourself, which are much harder than the SOD test, right? And just to show you this one, so it's Toro test number 2, right? It's a supersonic rarefaction wave. So you have 2 rarefaction waves, one on the left and one on the right, and they are supersonic. So you suck the air out of the room by moving very fast to the left and to the right. And you see the density is almost getting to 0 here in the middle. And the pressure also almost to 0. Right? And because this problem doesn't involve any shock, it's just one contact discontinuity in the middle and 2 rarefaction, one on each side, the entropy should be conserved. Right? There is no shock, so the entropy should be constant. And that's the entropy. The exact solution is the black line, and that's the numerical solution. Right? So you see, not good. And that's an example of failure, right? And you see you have this effect where the entropy is like shooting up at the initial discontinuity, and this is called wall heating. So basically, the numerical solution creates some spurious entropy just due to the initial discontinuity and the fact that the code doesn't handle that very well. Okay, and so you see that you should find 0.4, you basically find 2 in the middle, right? So it's not a few percent, right? It's like a factor of 3, actually 5. Anyway, that's a failure, right? And so the exact solution in blue is doing a little bit better than the Teyssier answer, but not much, right? So it's not a problem of Riemann solver. It's really a problem of the method itself. And actually, the problem, it's interesting. The problem is that the method is conservative. If you use a non-conservative scheme, for example, if you use the entropy as variable, then it would have been perfect. So it's an example where using the exact conservation law is actually worse than using the entropy. Anyway, so second order schemes, high order schemes. So here the idea is to give up on the piecewise constant representation here and to say, okay, let's try to do better. Okay, so the second step is to now replace your piecewise constant values by a linear value. So now your solution is given by a polynomial of degree 1, right? A line, right? And so you see that you have this guy here, which is ui bar, the same as before. That's the numerical solution. But you need also to introduce a slope, which is the slope of this linear profile. Right? And so you see, so that's a polynomial of degree 1. And later, again, time permitting, we're going to see polynomial of higher degree to approximate the solution with higher order. Right? But so far, we just have a polynomial of degree 1. So we need to compute delta u, this slope, in order to come up with a linear profile. So how do you do that? So again, what you have at your disposal is those piecewise constant values, which is your numerical solution at times n. You need to compute a slope. And so here there are not much, solutions at our disposal because you are sitting at cell I. You have basically one cell on the left, one cell on the right, and the cell itself. That gives you 3 options to compute a slope. Right? You have the right slope, which is using the right neighbor minus the cell of interest. You have the left slope, which is the left neighbor used to compute the slope. And you have actually the average of the two, or using the right minus the left over 2. That's a higher order. That's the higher order approximation of the slope. And those three are equally valid. They're all going to give you a slope. So this one is called Lax-Van Droff. It's the downwind slope, because remember in the advection equation, the velocity goes to the right. So in this case, it's a downwind slope. That's going to be unstable. Right? That's the upwind slope. That's going to be stable. And that's an average of the two. This one also going to be stable. Right? And I'm not going to justify why it's unstable in one case and why it's stable in the other one, but just believe it. Right? And so this one actually is the best. Why? Because it's stable, but it's also more accurate. It's a more accurate approximation of the derivative than those two. Okay, so that's usually the preferred one. Okay, so okay, great. So let's do that. Let's take this numerical approximation of the derivative and let's plug this in here. And then we have a second order accurate solution. So if you move to fourth order, that's just an example. Actually, it's very much the same idea, right? So you just need now more cells, either on the left or either on the right. Again, same problem as before, right? Except now you use 4 cells. So you use the central cell, xi, and then 1 on the left, 2 on the right, or 2 on the left, 1 on the right. And then those 4 cells can be used to approximate your solution using a degree 3 polynomial, right? With 4 points, you can set a degree 3 polynomial. And you can now approximate your solution at the interface using this degree 3 polynomial. And so the best like before, is by averaging the two schemes. So you get now a kernel with 5 points, right? And then that's what you get. So you see, you have these 5 cells who are now involved in computing the solution at the interface. And so the price to pay is that you have a much wider stencil. So the jargon here is stencil. That's how many cells you have involved in the calculation. There is a tricky point is that if you have a higher order scheme, you also need a higher order time integration. It doesn't work. I will come back to this in a minute. And we will see a catastrophe happening, is that higher order schemes are oscillatory. And actually, Godunov, the same Godunov as before, found a theorem, which is terrible, that states that everything which is more than order 1 will be oscillatory. And I will show you what I mean by oscillatory. Yeah.
So when you recover the primitive variables from concerned ones, do
Yeah.
you also change how you do that? Because earlier you were doing like just the average of the ratio, it's the ratio of the averages, which does not hold.
Exactly.
Right.
You're totally right. So that's one issue. That's one issue when you move to high order is what variable do you use to do this polynomial approximation. And so again, I think I have a slide on that. It's a matter of choice. But it's true that if you want to go to high order, if you really want your solution to be high order enough, you have to be very careful with this transition between conservative and primitive. Okay, so here we go. That's what I mean by oscillation. So here I have the first order. So this is the composite profile. This is the advection equation. So we just advect this weird profile in black, right? Which is this. So you have like kind of a very thin Gaussian. You have a square. You have a triangle, and then you have a wide Gaussian. And this is advected by a velocity 1 with periodic boundary condition until it goes one cycle around and then comes back to its original thing. And then when it comes back, that's the first order Godunov scheme. So it's really ugly, right? You see it completely lost. Everything is smeared out. Then you have second order Hancock. So those are variants, but focus on the green and the violet one. Second order and fourth order. And you see that it's better and better, but look at that. Right? So you have these oscillations, right? So things are really going crazy. Yeah.
So these like higher order schemes, when you're incorporating more interfaces into your algorithm, does that affect the CFL condition?
No. No. The only thing that changes is how you compute the value at the left and the right interface. And then all the rest is the same as I presented before for the Godunov method. The only thing that changes is this step, the reconstruction step, it's called. All the rest is the same. The courant factor is the same. But you need a higher order time integrator. I will come back to this in a minute. Okay, so ugly oscillations, and this is dramatic, right? This is not just, okay, it's oscillating a bit. No, because if your density becomes negative, that's it, you're dead. Your simulation stops, right? So this is not acceptable. It's not like, okay, we are a bit picky and we want exact results or whatever. No, this is a matter of life and death. Right? So if your density becomes like negative like that, you cannot compute the sound speed anymore. Everything goes crazy, right? So you need to solve this, right? And the solution comes from slow primitives, right? That's the magic here. So Godunov method, it's also called the Godunov theorem. It's also called the barrier theorem in the jargon. It means that you cannot do more than something, right? It's pretty bad in math when a theorem tells you that, you're really depressed. But the key point in Godunov theorem is that you have a linear scheme. So let me briefly go back. So what is a linear scheme? For example, if you adopt this slope, right, you see that your numerical approximation is completely linear as a function of the solution, right? So it's a linear scheme, meaning that you have linear dependency. This is also linear, right? You see that this is a linear, 20 times 10 plus whatever. These are linear operators. So if you have a linear operator like that, Godunov theorem tells you of if your order larger than 1, which is basically everything, then you're going to be oscillatory and your density will become negative. So that's pretty bad. But the key point is that the key assumption that you can try to circumvent is the linearity. If you can design a numerical scheme which is non-linear as a function of u left, u right, then maybe you can go around Godunov theorem and still find something which is non-oscillatory and positivity preserving, right, for the density. And so the idea is that you will replace, so that's the linear version of it, where delta u is given by the linear function of ui plus 1 and ui minus 1. You're going to replace this by a non-linear function that is called a slope limiter, which is between 0 and 1. And you multiply the linear slope by this phi. Okay, and now of course we have to find phi, of course, right? But if phi equals 0, then you're back to first order Godunov, and you know it's not oscillatory. Okay, so phi equals 0 is a solution, but then you're going to lose all the accuracy of the scheme, right? But at least you know that phi equals 0. If you adopt phi equals 0 at certain location in your solution, it might help preventing those oscillations. Ideally, you want to use phi equal 1 as much as you can, because then you know that you're going to be high order, right? But you don't, you know, so basically the idea now is to find this nonlinear function so that it does the job of being as close as 1 as possible, but cleverly switching to 0 to prevent those oscillations. Right? So there are actually 3 types of rules. First one, you don't want to create a new maximum. That's really, if you have a situation where the central cell is higher than the 2 other, any slope that you adopt will create a new maximum. So in this case, you want phi equals 0. Right? So if delta u left times delta u right is negative, meaning you have a maximum or a minimum, then set delta u equals 0. Right? So phi equals 0 in this case. So, okay, so now we consider a case where now the solution is monotonous. It's either growing or decreasing, right? So now how do we compute phi? So there is 2 solutions which are very popular. The first slope is called the mean mode slope limiter. The idea is that your reconstructed solution, the red solution, is strictly monotonous, right? So that you cannot overshoot. So for example, if you take this slope and you make it larger like that, and this guy, if this guy goes above this guy, no, you put phi smaller. Right? And so by just imposing this condition that you don't want the overshoot, you don't want those 2 guys to change sign, right? Then that's how you do it, right? So basically you write the left value here, that's this guy, you write the right value here, this guy, and then you ask this guy to always stay below this one, and you ask this one to always stay below this one. And if you write down, this gives you a condition that the slope has to be the minimum of the left and the right slope. If this condition is satisfied, you know that you're never going to be overshooting the value at the interface. That's called the mean mode slope limiter, right? There is another version of that, which is more aggressive. It's called the Monsen slope limiter. So here you allow for this overturn, so this switch. You say that's fine, but you cannot allow this guy to go above the piecewise constant value on the right. So you see, you're still limiting your solution. You don't want to go there, but you allow for this kind of a switch. Okay, and so if you do that, then that's the condition, right? So it's the minimum of 2 delta u left, 2 delta u right, and the from slope, the central slope. And you see that in this case, phi will be much closer to 1 in much more situations. So you see, you move from here, which is very conservative, to here, which is more aggressive, right? But at least you limit with the piecewise constant value. Okay. So, okay, I'm going to switch this. So now if you adopt this kind of limiting strategy, that's what you get. It's beautiful. You see so that's the second order scheme. This is just the second order scheme. You see min mode is there. So it's better than first order, but it's still quite diffusive. Monsen is up there in blue. And then the violet is another version, which I don't have time to discuss, right? So you see that that's basically what the slope limiter does, right? So min mode is really more diffusive than Monsen, right? You can see that it's not getting, as nice, but it's also more dangerous, especially with nonlinear problems. Okay, so time integration. So as I said, when you move to high order, you have to change the way you perform the time integration, because the problem moving to high order, as I said here, you can see that now your solution is piecewise linear. And the consequence of that is that the Riemann problem at the interface is not self-similar anymore. You lose the self-similarity of the Riemann problem that you had when things were piecewise constant. Because you lose the self-similarity, it means you cannot replace the flux by a constant value and take it out of the time integral. Right? Now you have to perform the proper time integration. So now your flux, so that's your flux, right? That's the flux, the time average of the flux. Now you cannot assume this is constant, take it out, and then get the value. Now this is not constant anymore, because your Riemann solution is not self-similar. Meaning, like now you have to perform the integral using a quadrature in time. So you approximate your integral by a quadrature, right? Basically, with a quadrature weights and quadrature points in time, right? And so now the key point is you have to compute the solution U at different times, right? And so this is kind of a predictor-corrector approach, right? So you basically start at times n. You try one first step to find your solution. Then you try again, and each time you get a new quadrature point. And at the end, once you have all the quadrature points with predictor values, you finally perform the final integration by doing the quadrature. So these are called Runge-Kutta schemes. I don't have time to do the theory of Runge-Kutta time integrator, but if you're interested, I can point you to some good reference. The key point is that you're performing this time integration up to a given order, which gives you the order of accuracy of your time integration. What's expensive here is that at each of these time quadrature points, you have to reconstruct the left and the right value at the interface using second order, fourth order, whatever, and solve the Riemann problem there. Each time you have to solve the Riemann problem so that you get the Godunov flux here at the current time coordinate. So that's expensive, right? So, okay. So that's the second order scheme, the most popular second order scheme there is for the Euler equation. So it starts very much exactly like the first order scheme. So you start with the conservative variable at times n, again, finite volume, average. You compute the primitive variable using the technique we did before. So we, just to come back to the question we had before, in this case, that's how you do it, right? You compute the sound speed, you compute the time step. So far, exactly like the first order Godunov method. Then you have to compute the slopes. Forget about the smooth extremum. You compute the slopes for each of the variables. So here there is a freedom. You can use either the primitive variable or the conservative variable. It's not going to be that important, but primitive variable versions are actually better. So you compute the slopes here for the density, the velocity, and the pressure using the slope limiters. And then you perform a predictor step. So you compute, and that's the quadrature point, the time quadrature, right? At the time step n plus half, or t plus delta t over 2. So the way you do it in the muscle scheme is you just use this quasi-linear form of the Euler equation to guess what will be the solution at delta t over 2. Right? Once you have the solution at delta t over 2, which is here, then you reconstruct the variable at the left and the right face using the slopes, the limited slopes, and then you call the Riemann solver, compute the flux, and you have the final update. Okay, that's the muscle scheme. So as I said, right, you have freedom to use different variables to do this slope limiting, right? So as I'll show you the example with primitive variable, but you can also use the conservative variable. Some people do that, so they don't transform the conservative into primitive, they keep the conservative, and they use the slopes on the conservative variable. But there is another version, which is even more sophisticated, is to use the so-called characteristic variable, which are the eigenvalue of the Euler Jacobian matrix, right? Remember what we did before? You compute the Jacobian matrix, you perform the eigenvector decomposition, and then you compute the coefficient of your solution, alpha, the alphas, on these eigenvectors, and then you use the slope limiters on those guys. Right. And why is it interesting to do that? Remember, if you perform this eigenvector decomposition, your problem is now transformed into 3 independent advection problems where you have 3 advection waves. And so this is much cleaner because this is really 3 independent simple advections. And then you can do the slope limiting on those. So that's much more sophisticated. Seriously, I strongly, the take-home message is just use primitive variable and forget about it. But anyway. And then finally, the Riemann solver to compute the flux. Okay, so that's the summary, right? So that's the predictor step. So basically, you can combine what I explained earlier into one thing where A is the Jacobian matrix. So you have, and the deltas are the limited slope. So you get the left and right face. And now you see that now the left and right state of the Riemann solver are not cell average anymore, right? They are point values at the interface, I plus half, right? So that's the difference with the first order Godunov scheme, where the left and right state are the cell average values. Now those are the reconstructed values at the interface. That's where you get the extra accuracy. And once you have the flux, then you update the finite volume quantities the same way. Okay, so now let's see how it works. So you have the second, so this is muscle versus first order with 100 cells. And so now you see the blue is the second order scheme. Look at that. I mean, the rarefaction wave is really much better. Right? And the contact discontinuity is also significantly better. And that's Monsen, by the way. I think I used Monsen. Yeah, that's the Monsen slope limiter, the more aggressive one. But you see that the solution is beautiful, right? There is no oscillation. And look at that. So the shock is the same. The shock doesn't change. Right? The shock was perfect already, so it's nice. It's perfect still. But the contact discontinuity is game changing. Yeah? And the rarefaction wave is pretty good. So, okay, now how are we doing now for the entropy in this very difficult supersonic rarefaction test? Wow, look at that. Bam. Right? So pretty good, right? Well, it's still bad, but pretty good. Now we're a factor of 2 point something off, right? Okay, so okay, what's interesting now, if you move to second order, is that the choice of the Riemann solver seems to be not so important anymore, right? So you see the different Riemann solver. Okay, clearly the contact discontinuity, it's still actually better to use HLLC or exact because the other one are a bit diffusive for the contact discontinuity. But otherwise, I mean, you don't really see any difference, right? Okay. So now I will show you briefly the fourth order scheme. So I'm gonna fly over this. I'm gonna show you the results. So that's the fourth order scheme. So okay, the contact discontinuity is even better, right? But the rarefaction wave is almost perfect. Right? So that's pretty good. Let's see what the entropy does. Yeah, look at that. much better, right? So that's actually quite spectacular, right? So it means that going to high order help you more and more. But of course, one thing that you have to realize is that this fourth order scheme is like way more expensive, right? So of course, there is a price to pay, right? Which is a much slower kind of algorithm. But in this particular example, it's worth doing it. Okay, now the very important point here is that now the Riemann solver has no effect. And why is that? Because now the solution is such better quality, fourth order, right? That actually you can use your shittiest Riemann solver, it works. Right? And so what it tells you is that the fourth order scheme is expensive, yes, but you can really use your fastest Riemann solver, it's good enough. So you don't even need to use HLLC anymore. If you use the fastest one, which is LLF, which is like almost nothing, right? It's like one line. You capture the solution pretty well, right? So that's an added value. So okay, fourth order or even higher order, it's expensive, but it allows you to use the fastest Riemann solver. And the reason it doesn't make a difference anymore is that your solution becomes less and less discontinuous. Right? So your Riemann solver is less and less useful. So now you could say, okay, but I mean, fourth order, look at the contact discontinuity, it's still pretty smeared out, right? And it's true that the added value between second order and fourth order for discontinuities is not, that much. It's probably more efficient to use your second order schemes and just double the number of cells. That will be much more efficient, right? To capture the discontinuities. So the main added value of the fourth order method is for smooth solutions. And so here I show you an example of the advection of a sine wave. So in black, that's the initial condition, right? And then you have first order is the red, right? So here what I do is I advect this sine wave, but not once, but 100 times, right? So that's the time is 100. And so after 100 orbits, the first order solution is basically zero, right? So everything has been diffused away and there is nothing left, right? The second order is the green one. It's still, sinusoidally, but it's totally wrong in terms of phase and the amplitude has decreased. The third order one, the phase is correct, but the amplitude is kind of, the fourth order one is perfect after 100 orbits. And so that's really the added value of going to higher order. And when you have smooth solution, you can really preserve them and like forever. And you need to go to, I think you need to go to 10,000 orbits to start to see an effect on the fourth order. So it's really, really the main added value of going higher order is for this long time integration of smooth solution. For discontinuities, actually, there is a better technique called adaptive mesh refinement. Right? And I think you're going to see a lot of examples this week. So the idea is to refine adaptively the grid so that you don't have a uniform grid anymore, but you put more cells where your solution requires it. Right? And so this is called also H adaptivity. H because you have the cell size H. There is actually, when you combine this with higher order method, there is a very cool idea, which is called HP adaptivity. So when you have, for example, a smooth solution like that, then you can use large cells, but a higher order method. So P is the polynomial degree, has to be chosen high, but H, the cell size, can be very large. So it's cheap. It's actually cheaper. But on the other hand, if you have a discontinuity, you want to use small p, but a very small h. Like p equal 1 is probably enough, second order method, but with very small h, right? So you use AMR in this case. Right? So that's kind of the idea, is to choose which method is the best, either refining the mesh, low order, second order, or increasing the polynomial degree, but using large meshes. So this is an example of AMR. So there is I don't know, there is like probably 100-ish cells here. But you see that they are very spaced out there when things are boring. And there's a lot of cells here at the contact discontinuity. Right? And so you see that the discontinuity in this case is totally perfect. Right? It's like vertical. A lot of cells, right? Right? You have like 6 cells. It's a lot. But they are so small that the solution is perfect. Right? And the shock, there is 0 cell in the shock. Even better. Probably by luck. Oh, no, there is 2 cells. There is 2 cells are here. So okay, now if you look this problem, right, with AMR, doesn't help. AMR doesn't help, right? You see that it's a second order scheme here. So you see you get the same weird wall heating effect even with AMR. So it's just thinner, right? You manage to make it to squeeze the wrong region much more, but the amplitude is the same as without AMR. So AMR doesn't help at all in this case. What helps is going to high order, like we have seen before, right? So that's an example of, AMR is not helping. Okay, I think, well, I have a few minutes. Going to multiple dimension is very easy in the Godunov methodology. The only thing you have to change is your definition of what it means, finite volume. In this case, in 2D, for example, it's a 2D advection equation. And now you have a double bar because it's a double integral, right? And so your finite volume approximation now is an integral in the little square, right? So that's the first change, the definition of what we mean by volume average. And the second change is that you can write the same kind of time space integral form, except now you see that the fluxes that are shown here are now time average like before, but also line average, because you have to average along each face of the square, right? And so that's the big definition, the big change compared to 1D, is that in 2D you have now this integration to perform along the face, right? But the update, the finite volume update, is the same as before, right? Except that now, so it's still exact. It's an exact integral form. But the tricky business is that you have to compute a time and a spatial average of the flux. And so I don't have I'm out of time now, but the idea is that you will replace this integral by a quadrature in space, like we did for the time. Right? So now you have a quadrature in time and a quadrature in space, and you're going to end up with many, many Riemann solvers, and it's going to be more expensive. Right? So I'm going to leave you here. And yeah, this is all okay. And these are my conclusion slides. Very briefly, so I presented Mussel-Hancock, which is a second order scheme, strictly conservative. Monsen slope limiter is the best. You have to use HLLC in this case because the Riemann solver matters. Fourth order scheme, very good for long-time integration of smooth solution. You need a Runge-Kutta method to update the solution. You don't need an expensive Riemann solver. Lax-Friedrich is enough. Right? And then we have seen AMR. So you need HLLC. You need to put your resolution locally very high. And we're going to use the Ramses code and the Athena code tomorrow to do these kind of calculations. That's it. Thank you.